So last lesson we talked about measures of central location, and the way we described it was we were trying to come up with one number to describe a typical whatever. Another name for typical could be average. This lesson what we're looking at is something called measures of dispersion. So what we're looking for is one number to measure how close together all the values in our data set are, or how spread out they are. And it's important because when we talk about finance and money, the way we measure risk is how spread out our returns are. So our measure of dispersion, when you go on and take other finance and accounting classes, will become our measure of financial risk. So the example should look vaguely familiar. I just changed a few words. You'd like to sell real estate when you graduate from college. You go to a real estate firm and ask how many houses you can expect to sell per month. The busy manager gives you a sample of the realtor's sales in houses for the past month. So 75341005. Last time we tried to describe what a typical monthly sales was, and we said that it was close to 5, 4.84 for the mean and 5 for both the mode and the median. Now we're trying to come up with one number to measure how spread out these values are. And we're going to look at 4 candidates, which is really 3 candidates and 1 candidate changed. And the first one that we're going to look at is something called the range. So here's our 7 numbers. And to calculate the range, what we do is we just take our highest value and we subtract from that our lowest value. So the most sales was 10, the least sales was 0, our range is 10. So on an exam, your range should be one number. Don't tell me it's between 0 and 10. Just give me the actual value. Now, this is an easy number to understand. It's an easy number to calculate, but it has a number of shortcomings, 2 big ones that I can think of. And the first most important one is it doesn't use all the values. It's only using 2 values on our data set of 7. So not as big a deal for 7, but imagine we were looking at 30, 40, or 50. We're only using 2 values, and that the second point falls out of that. Even worse, we're using the 2 most extreme values. Now there's other measures of dispersion that we don't talk about so much in this course, like interquartile range, where instead of looking at the 2 most extreme values, we look at the value a quarter of the way through and a value 3/4 of the way through and find that distance. So range is kind of a quick and dirty way to measure dispersion, but it's not the best. So we want a measure that's going to use all our values. And the measure that we're going to focus on in this class is something called standard deviation. And there's 2 standard deviations that we'll talk about. The first one is standard deviation of a population, and that has the symbol sigma. And that's equal to all under the big giant square root sign. X minus mu squared, all divided by n, and then take the square root of that. Variance is just the standard deviation squared. So if we were to take our standard deviation number and square it, we wind up with variance. Most textbooks, when they teach, always ask you for the variance number first, and that's because the textbooks are solving by formula. We're going to use our calculator. And variance is a number that you get to on the way to calculating standard deviation. If our data set was a sample, the symbol would change. It would be S instead of sigma. Still be x. Instead of minus mu, it's minus our sample mean, which is x bar. And the big change, and this is all under the square root sign, is instead of dividing by capital N, which is the number of values in our data set, we divide by n minus 1, which is the number of values in our sample data set. So the population standard deviation will always be a little bit smaller than the sample standard deviation. The reason for that actually isn't trivial when we go and talk about yn versus n minus 1. But a way to remember it is, with the sample standard deviation, you not only have the variation in your data set, but you have this extra variation because your data set's only part of the population. So using that logic, the sample standard deviation should always be higher because there's more variation than the population standard deviation. And our symbol for that would be s squared. So if we look at the formula and talk about how it would actually work, what we would do is we would take each individual value, subtract the mean from it, square that value, add together all those numbers. So you see, one of the things I forgot, which you probably caught, is we need to sum these values together. So I'll put in the summation sign. So then we would add them all up together, and then we would sort of find the average deviation by dividing by n, or n minus 1 in the case of a sample standard deviation. And then we'd wind up with a huge number, which would be our variance, and we would take the square root of that to come down to our standard deviation. So you still might be asking, well, what the heck is a standard deviation? Well, a standard deviation is a measure of how spread out your data points are. Imagine that all your values were the same. Well, then your standard deviation would be 0. As your standard deviation changes and gets higher, your mean would stay the same, but you'd have some higher and lower values. So one way to think about the standard deviation is you can almost think of it as the average distance from the mean. But the reason that that's not a perfect way to think about it is because we square that difference. So what that does is it makes extreme values, values that are way above or way below the mean, count for a lot more. It's like a weighted average where values farther away from the mean are weighted higher. So let's actually do this on our calculator. So we'll go back and we'll have a look at our data set. And there's our data set, 7, 5, 3, 4, 10, 0, 5. We'll break out our powerful calculator. And we'll move it away from the data set. So what we're going to do is we're going to clear our data. So we're going to go second data, which is second 7. And then it looks like it's clear, but I'm not going to trust it, and I'm going to clear it anyway. So second clear down in the bottom left. Now I'm going to enter my data values the same way we did for the mean. In fact, it's exactly the same procedure as we did for the mean. So I'm going to go 7, enter, scroll through to the next x, 5, enter, scroll through, 3, enter, and I'm just going to stop talking now. And now all our data values are entered. We're going to go second stat, which is second 8. We're in lin mode. If you weren't in lin mode or 1v mode, you just go second enter to change the mode. What the heck, I'll show you. That's log mode, we don't want that. Exponential mode, no. Power mode, no. That would work, but we'll stick with lin mode, which is what your calculator would have as its default. We scroll down. N is equal to 7. We scroll down again. X bar is equal to 4.857142857. That's from last lesson. And I'm going to store it because I'm going to need it later. So I'm going to go store 0. And my X bar is saved as 0. And then I'm going to scroll down again. And there's my sample standard deviation, 3.132. So I'm going to go store 1. And I've saved that. And if we scroll down again, we'll see that it gives us the population standard deviation. So you have to know whether what you're looking at is a sample or a population. Just about everything we calculate is going to be a sample standard deviation. The big exception is when we're doing a probability distribution. So populations are huge, and normally we don't have the resources to take a census, which is getting all the population data. Okay, so let's go back. Before we do go back, the next question says variance. So remember, variance is just our standard deviation squared. I'm going to take our standard deviation, 3.132, and I'm going to hit squared, and I'm going to get 9.809. So if I go back, my standard deviation is 3.132, and my variance is 9.809, or 9.810 if we want to round. So sorry, that was my standard deviation. Watch this, I'll fix it. And my variance is 9. Now the last thing that we were to calculate was the coefficient of variation. And the coefficient of variation is your standard deviation divided by your mean, all times 100. So if we were to do it for this problem, we would wind up with 3.132 divided by, I think our mean was 4.84, but I may have to correct myself. And let's go enter that into our calculator. Multiply it by 100 when we're all done. We'll recall 1, which is my standard deviation, divided by recall 0, which is my mean, equals, and I'll multiply it by 100. And I wind up with 64.48. So this was actually 4.86. And this is equal to 64.48. So textbooks are different on how to present this number, but in all textbooks it's really the same thing. You're expressing your standard deviation as a percent of the mean. So some textbooks want you to add a percent sign to this. Others say never add a percent sign. It doesn't really matter. What we're saying is that our standard deviation is 64% of the mean. And the way that this number becomes really useful is we use to compare variation, which is another name for dispersion or risk, when we have different sizes or different units. So let's go back to our PowerPoint and we'll have a look at an example that's just like this. So 64.48 was our coefficient of variation for sales of houses. It says the manager also gives us the commissions for 7 salespeople. The values are given below, and we're going to assume this is a sample, that they have more than 1 month of data and more than 7 salespeople. And the question is, which has more variability, the sales in houses or commissions? Well, when we're trying to compare variability, the first number that we start at is standard deviation. So let's put this into our calculator and calculate the standard deviation. So same thing, I go second data. Didn't like the second data. And then I go second clear. Okay, so now I'll enter my data values in, 4,000, enter. Remember, I'm just going to enter them in as my x variable. 6,000. 8,000. Not 80,000. 10,000. 3,000. 2,000 and 5,000. Now I just have to go second stat, Lin mode, which is good, 7 numbers looking good. Our mean is 5,428.57. I'm going to store that because I know I'll need it, so store in 0. And our standard deviation when we go down is $2,820 basically. So, which has more variation? Well, if we use the standard deviation, it's no contest, 2,819 versus 3.132. So we'd say, obviously, there's way more variation in commissions. But commissions is in dollars, sales is in number of houses, different units. The average number of sales is 4.86. The average commission is 5,200 or 5,400 and change. So we can't just compare standard deviations because we've got different units and way different means. So what we're going to do is find the coefficient of variation. So there's my standard deviation. I'm going to go divided by, and then I'm going to go recall 0 where I put my mean, equals, and I'll multiply it by 100 times 100 equals 51.95. So remember, for sales and houses, our coefficient of variation was 64.48. For commissions, it's 51.95. So actually there's more variation in house sales than there is in commissions.